Hi everyone, it's me, Dr. V, and it's a good day to do some AP Chemistry exam review. In this webcast, we're going to go through free response question number 3 from the 2024 exam. Now, with the 2025 exam coming up, there are some things you should know. In case you're not already aware, this year's exam will be given as a hybrid exam, which means the multiple choice questions will be done completely online in the Blue Book app. The free response questions will be presented to you online, but you're going to write your answers on paper in a paper answer book. Other things to keep in mind is that you will have a paper periodic table for the entire test. There'll also be a digital periodic table available to you. The reference sheets, that formula sheet, however, will only be available digitally. You'll have to pull it down in Blue Book every time you want to open it up. The other thing to point out is that you will have access to the online Desmos graphing calculator in Blue Book. You'll also have use of a handheld calculator, not a phone. It's got to be an actual calculator. Let's talk about what we're going to do in this webcast. Free response question number 3 is one of the 3 long free response questions in the AP Chemistry exam. That means it's scored out of 10 points. And these long free response questions have multiple parts, 7, 8, 9 parts sometimes. And they're going to switch topics several times during the question. It's an example of what I call a kitchen sink question. Be ready to shift gears. Before you go any further, grab your calculator, your periodic table, your formula sheet, some paper to write down your answers. What I want you to do is to listen to me introduce each part of the question and then pause the webcast and try to answer it on your own. And then listen to my explanation of how I arrived at my answer. And then keep track of your score as you go for each part. Did you earn the point? Did you not earn the point? And that's going to really help you develop as an AP Chemistry student. The goal here is for you to show your knowledge on this really big exam, and you want to make sure that you're doing everything you can to earn the credit for what you know. All right, let's jump right into the question. Sterling silver is an alloy that is commonly used to make jewelry. It consists of 92.5% silver and 7.5% other metals such as copper by mass. Over time, the alloy can form a tarnish of silver sulfide when it reacts with hydrogen sulfide, as represented by the following equation. Part A of the question says, what are the oxidation numbers of silver in silver metal and in silver sulfide? Well, for silver metal, the oxidation number is 0. Hopefully you know this already, but pure elements always have an oxidation number of 0. It's worth knowing that. For the silver in the silver sulfide, it's +1. The common oxidation state, the common charge of silver ions is +1. That would be its oxidation number here. You had to have both of these correct to earn the point for part A. The question goes on. The following table contains the atomic radii for silver and copper. And the next part of it asks, explain why sterling silver is better classified as a substitutional alloy than as an interstitial alloy. So alloys are mixtures of metals. What we notice if you look at the table is that the radii of silver atoms and the radii of copper atoms are really similar in their value. They're not that different. And this would be a substitutional alloy. What do we mean by a substitutional alloy? Well, what we see is that some of the places of one metal are replaced by another metal that's similar in size. Whereas an interstitial alloy, what we see is that we have metals with very different radii, and the smaller atoms fit in between the spaces of the other atoms. And that's what we call an interstitial alloy. And that's what you needed to say for one point. You didn't have to have diagrams of substitutional versus interstitial alloys. I'm trying to make sure everyone knows what's going on here. Using principles of atomic structure and Coulomb's law, explain why silver has a larger atomic radius than copper does. So this is a very specific hint that they're giving you. Atomic structure means you should be talking about energy levels. And Coulomb's law means you're talking about a force of attraction between oppositely charged particles. For copper, thinking about the end of the electron configuration, the last electrons are occupying the 4s sublevel and the 3d sublevel. For silver, which is one row down in the periodic table, the electron configuration ends with 5s and 4d. Its last electrons are going into the 5th energy level and the 4d sublevel. So what's important to state here is that the silver atoms have more occupied energy levels than the copper atoms have. That's a really important statement. One of the common mistakes we see here is students will talk about the number of orbitals. It's the number of occupied energy levels that's really the critical piece here. And when they say principles of atomic structure, you're either talking about numbers of occupied energy levels if you're talking about group trends, or if you're looking at a period trend, you're talking about the nuclear charge. That's what you need to focus on. And then Coulomb's law is again about those attractions. The electrons in energy level 5 for silver are farther away from the nucleus than the electrons in energy level 4 for copper, which means the outermost electrons for silver experience a weaker Coulombic attraction to the nucleus compared to the outermost electrons of copper being attracted to the copper nucleus. Those are the critical points you need to make to earn the point here for B part 2. The silver sulfide tarnish on sterling silver can be removed until only sterling silver remains. A student weighs a tarnished sterling silver sample both before and after removing the silver sulfide. We're given the molar mass. How nice. And records the data in the following table. So the mass before the tarnish removal and after the tarnish removal. Assuming that only silver sulfide is removed, calculate the number of moles of silver atoms removed. The first thing we need to do here is calculate the mass of silver sulfide that's removed. We know the mass before, we know the mass after. The difference of those would be the mass of the silver sulfide that's been taken away. We're asked to find the moles of silver atoms. So we know the mass of the silver sulfide. We're given the molar mass, as I mentioned before, so we can convert that to moles of silver sulfide. But that's not what we're solving for. What you have to notice here is that for every mole of silver sulfide, there are 2 moles of silver. And we have to use that conversion factor to get our final answer, which is 0.08289 moles of silver atoms. And we do actually know that to 4 sig figs. There are 2 points for part C. 1 point was for finding the mass of the silver sulfide that was removed and doing that correctly. And then the second point was for finishing the calculation with the correct answer. You do need to show all your work here, and of course you want to arrive at the correct answer. But there was an opportunity for some partial credit. Oh, it's a kitchen sink question. Look, we're totally shifting gears here. Rhodium plating is a process used to protect sterling silver from tarnishing. This involves electroplating or depositing solid rhodium onto the surface of the metal from an acidified solution of rhodium-3 sulfate. Oxygen gas is produced during this process. A table of half reactions related to the overall reaction is provided. So we just have the half reactions that are involved in this question. So we have a rhodium half reaction and we have an oxygen half reaction. Write the balanced net ionic equation for plating rhodium metal from the acidified rhodium-3 sulfate solution. The key here is to read the question carefully. They're actually telling you exactly what's happening in this process, giving a really big fat clue here. We're electroplating solid rhodium. We're depositing solid rhodium onto the surface of the metal. So when we look at that rhodium half reaction, that's telling us that we need rhodium as a product. So we're going to keep that half reaction as written. And I'm going to just copy it down. And if you go on and read the introduction to this part of the question, it also tells us that oxygen gas is produced during this process. Oxygen is produced. Oxygen is a product. So when we look at the oxygen half reaction, the other half reaction, we need to flip it because we need the oxygen as a product. So I'm going to write it down reverse from what was given in the table. Now, the other thing to keep in mind is when we are writing overall equations for redox processes, the number of electrons lost has to equal the numbers of electrons gained. I can't have electrons in my overall reaction. They need to cancel out. So what I need to do is multiply the rhodium half reaction by 4. And I'm going to multiply the oxygen half reaction by 3. That gives me 12 electrons in each half reaction, and those electrons will cancel out. And then I can add up my 2 half reactions. And here's my final equation. 4 rhodium-3 ions plus 6 water molecules give me 4 rhodium atoms plus 3 oxygen molecules plus 12 hydrogen ions. I don't have to have the states of matter in my final answer, but this is what I needed to do to earn the point for part D part 1. D part 2 goes on and says, calculate the value of E cell for the reaction that we just wrote, which I've got here. Now think about what we know. We know we're keeping the rhodium half reaction as written. We flipped the oxygen half reaction. Now we know that electroplating is an electrolytic cell. This is, again, another clue. They're really helping you out here, all right? It's an electrolytic cell, and you should know. And if you don't, I'm going to tell you right now, for an electrolytic cell, E cell is a negative value. All right, it's not a spontaneous process. And so the other thing to keep in mind, since we know we're flipping the reaction involving oxygen, we have to change the sign of that E naught value to find E cell. And then we're going to add them up. So we get an E cell of negative 0.43 volts. It's an electrolytic cell. We should be getting a negative cell voltage here. The other thing I want to remind you is when we're finding E cell, you never ever multiply those E naught values by coefficients. And that's true whether it's a galvanic cell, an electrolytic cell, you don't do it. So we're just going to add those numbers up. You had to have a value of 0.43 volts to earn the point here. Based on your answer, explain why this process requires the use of an external power source. Now, we just found E cell. It's negative 0.43 volts, right? We've said that a bunch of times. But we know this is an electrolytic cell. E cell is less than 0, which means delta G is positive. It's not a spontaneous process. It's not thermodynamically favorable, to use the College Board's preferred terminology. It's not thermodynamically favorable. It needs a sustained energy input in order to proceed. That's why we need an external power supply. They're giving you a lot of hints about what's going on in this problem. But that's what you needed to say to earn the 1 point for D part 3. And there's one more part. Calculate the length of time in seconds required to plate 2.8 grams of rhodium metal onto a piece of sterling silver if 2.0 coulombs per second of current is applied. I really think of these kinds of problems from a dimensional analysis standpoint. But let's work through it. We need to plate out the rhodium metal from that solution containing rhodium ions. The half reaction that really matters here is the reduction of the rhodium ions to rhodium metal. We also need to remember that amps times seconds gives us coulombs. And we know the amps. We're given 2.0 coulombs per second for the current. We also remember the Faraday is coulombs per moles of electrons. There are 96,485 coulombs per moles of electrons. The Faraday, you might want to look that one up in your formula sheet. It's worth taking the time to do that. I wouldn't try to memorize it. It's how many moles of electrons are needed to reduce the rhodium-3 ions to make rhodium metal. 2.8 grams of it. So I can look at my periodic table, I can convert my grams of rhodium to moles of rhodium metal, and then I know from the half reaction that for every mole of rhodium that's deposited, 3 moles of electrons are required. So I can stop here and get 0.016 moles of electrons. I'm not worried about sig figs right now because I'm not done with the problem, so I'll keep going. And then from the Faraday, I can calculate coulombs. I can multiply my moles of electrons by the Faraday. I get 7,873 coulombs. Again, I'm not worried about sig figs. I'll take care of that at the end of the problem. I know that amps times seconds equals coulombs, so seconds would be coulombs divided by the amps. I found the coulombs. I'm given the amps. I'm going to substitute that in, and now I'll take care of my sig figs. 7,873 divided by 2 gives me 3,900 seconds. And I do want to report that with 2 sig figs because I knew my initial mass to 2 sig figs. I knew my amps to 2 sig figs. I encourage you to round at the end. So there are 2 points for part E. 1 point was for finding the moles of electrons, which might have been embedded in your other calculations. It might not have been a standalone piece. And then 1 point for finding the seconds and doing that correctly. How did you do? In 2024, the average score on question 3 was 4.42 points out of 10. So if you earned 4 or 5 points, you're right on track. You're at or above the national average here. If you earned 6 or more points, you're doing very well. If you didn't get the score you wanted, think back about some of the core ideas in this question. You needed to be able to do oxidation numbers. You needed to talk about periodic trends. You needed to be able to talk about alloys, substitutional versus interstitial alloys. And there were a whole bunch of redox questions. You had to write an ionic equation. You had to find E cell. You had to do a electroplating deposition calculation. So lots of different skills here. So if you miss those, you might want to go back and review it because they're extensively tested on the AP Chemistry exam, and you should expect to see it in May. If you found this video to be helpful, like the video and leave a comment, and remember to subscribe to my channel so you get all my latest updates. Have a great day and keep studying chemistry.